Okay, good morning, friends. Last class we started with signal conditioning devices. Just to recollect, uh, whatever signal we get from sensor and transducer, it should be properly conditioned or properly processed so that it can be used by the actuator in a mechatronic system. So we discussed operational amplifiers in the last class. So like operational amplifier as the name indicates, it amplifies the signal. Then after operational amplifiers, we'll be studying some of the conversion devices, like A to D converter is there, D to A converter is there. There are some other signal modifying devices as well. So in that series of signal conditioning devices, last class we started with simple construction of operational amplifier. Just to remind you, operational amplifier has got very high gain, so it can give amplification, very high amplification, and the input impedance is also very high, so it doesn't consume much power also. So the operational amplifiers are used even today for signal amplification purposes. So we studied the construction of a simple operational amplifier. Then we saw the applications of amplifier as a summing device, application of operational amplifier as a subtracting device in the last class, how we can use these operational amplifiers for our signal conditioning or mechatronic applications. Uh, if I have got two different sensors, three different sensors, and these sensors are giving the output voltages, and if I want at the summing point of my control system, if I want these signals to be added, and if I'm interested in amplification, I'm interested in summation of these input signals, then I can make use of operational amplifier as a summing device. Similarly, if I want the operational amplifier be used as a comparator, like a subtracting device. I have the set temperature value or the set pressure value that is in my mind, and from the furnace or from a thermal device, I am getting a feedback signal from a thermocouple. I want to have set temperature of say 300 degrees Celsius, and I want to, presently I have temperature of 250 degrees Celsius. So there is a deficit of 50 degrees Celsius. So what my transducers can do, my transducer can sense the temperature within the system, convert it into equivalent voltage form, and it will send it as a back signal. And corresponding to 300 degrees Celsius, I have got some voltage signal. So that voltage signal is to be compared with whatever is the feedback signal. And in that case, 3 volt minus 2.5 volt. So 0.5 volt is the error. Maybe it corresponds to 50 degrees Celsius. So this subtraction work of the input signal with the feedback signal can be done by using OpAmp. So OpAmp can be used as a comparator even. And then whatever is the error signal, that can be amplified further, and that amplified signal can be given to the actuating signal, maybe a heater in this case, or a temperature control system. And accordingly, the temperature of the system rises till I attain 300 degrees Celsius. So this OpAmp can be used as a comparator. Uh, Similarly, we have operational amplifier being used as an integrator. Now, how this can be used as an integrator? The circuit is shown here. So you have this basic operational amplifier. Remember, this amplifier comes in the form of, practically in the form of an IC. Maybe IC 741. There are a number of ICs, uh, integrated circuits, which have OpAmps in it. So this is my inverting signal of my OpAmp, negative sign. And this is non-inverting signal of my OpAmp. So these are the inputs to this OpAmp, and this is the output from the OpAmp. So to this inverting terminal, I give the voltage input. Okay, and I have one series resistance in between, and I take the voltage output from this terminal. Other terminals are of course grounded. So with respect to ground, I'll be getting some output voltage, and with respect to I'm giving some input voltage. Okay, so that output signal is fed back through a capacitor to this inverting signal. Now, last class we saw because there is a very high impedance at the input level of the OpAmp, virtually no current is flowing into this OpAmp. So X is virtually at 0 degree. Sorry, X is virtually at Vx is equal to 0. Okay. So if we see, there are two circuit loops. Current I flowing in this branch of the loop. There is a supply voltage, and current I is flowing across R and the operational amplifier. As I said, there is no current consumption at operational amplifier. So the signal will come back. The I will be flowing through this circuit. So this I will be flowing through resistance R. So Vin will be equal to I into R. Now that I, the same I, will be flowing through this circuit also, isn't it? So there is a second loop. So we have the first equation as Vin is equal to IR. So I will be equal to Vin by R. Take a pen and paper and draw this circuit and write this loop equation. This is the current I that is flowing here. Okay. So I will be equal to Vin upon R. Now similarly, in the second loop, the same I is flowing. Okay, and the output voltage is V out. Now what is the current that is flowing across I? So if we want to write equation for potential drop or voltage drop across capacitance, V out will be equal to 1 by C integral of I dt. 1 by C integral of I dt. So V out, write down, V out is equal to 1 by C. Now what I do is I convert this integral sign into 1 by D sign, operator form. Okay. So integral from T1 to T2 corresponds to 1 by D. So what will be the equation for output voltage across this capacitance? V out will be equal to 1 upon CD. What this D corresponds to? Integral sign, 1 by D. 1 by CD into I that is I dt. Okay. So I have V out is equal to 1 by CD into I. So if I solve it for I, second loop, what it will look like? I will be equal to CD into V out. CD if I take on the left hand side, CD into V out. Okay. So if I equate these two equations, what I get? I get relationship between V out and V in. Okay. Let us take a piece of paper. If you have drawn this circuit, fine. It's very simple. Remember, this is my OpAmp, a triangle sign with two inputs, one inverting input and one non-inverting input, and then one output. It's very simple construction. So this show one resistor here and show one capacitance here. Okay. So listen, the current is the rate of moment of charge Q, and since for a capacitor the charge Q is equal to C into V, where V is the voltage across it. Okay, then the capacitor I is equal to dQ by dt is equal to C into dV by dt. Okay, now V in our case is V out now. Okay, V out by dt. Okay. The same thing, whatever I told you just now, it is if I take this C on left hand side, take this dt on right hand side, on left hand side, what will happen? C will go on this side by 1 by as 1 by C. 1 by C I into dt is equal to dv out, isn't it? Understanding? I is equal to C into dv by dt. Okay, take this C on this side, so it will be 1 by C into I. Take this dt on the other side, so it is 1 dv out is equal to 1 by C I dt. So dv out is on the left hand side. So if we integrate both the sides, what will happen? dv will become v out. V out will be equal to 1 by C integral I dt. That's what I told you. Okay. So ultimately dv out will be equal to 1 by C 1 by CD into I. The potential difference across C, is virtually zero because of high impedance device. There is no current passing through it, so Vx is equal to 0. So since Vx is effectively 0, being the virtual earth, it is minus V out. So this V is nothing but minus V out. There's a current through the capacitor is minus C dV out by dt. But this is also the current through the input resistance. Okay. So what I told you, this I on the input loop is V in upon R, and this I across the output through the capacitance is I is equal to, just now I told you, I is equal to CD, right? So I is equal to CD into dV out. Okay, CD into dV out. So D, what is D? D is operator D upon d by dt. So CD V out. So if I equate both the equations for current I, because the same current I is flowing across input as well as output. So V in by R is equal to minus C into dV out by dt. C, rearranging and solving for dV out. Rearranging and solving for dV out. What will happen? dt is taken on left hand side. C minus C is taken on left hand side. It will go as 1 by RC. So minus 1 by RC into V in into dV, isn't it? So this C in the denominator 1 by RC minus sign. So minus 1 by RC into V in into this dt will be dV out. Okay. So integrating both the sides, what we get? dV out, integral of different side. These two are constants, R and C. 1 by RC is a constant, so that will remain outside. So if it is integrated, because it's function of time, integrating from T1 to T2. So V output at T2 minus V input, V out at T1. So if I integrate it, what will be the integration? It will be V out evaluated from T1 to T2, isn't it? So V out at T2 minus V out at T1 will be equal to, this is the constant, minus 1 by RC integral of V in dt evaluated from T1 to T2. Okay, so V out T2 is the output voltage at time T2, and V out T1 is the output voltage at time T1. The output is, this output is proportional to the integral of input voltage. Output voltage is proportional to, this is the constant of proportionality, proportional to integral of input voltage. That is the area under the graph of input voltage. Okay, so this is how the OpAmp can be used as integrator. Friends, what is the meaning of integrator? Integrator is nothing but summation of the signals evaluated from T1 to T2. So when I use this OpAmp as an integrator in my control circuit, what I'm doing practically, I'm giving some input. And what I want is at the output end of the OpAmp, what I want is, suppose the temperature signal is converted by the thermocouple into voltage signal. So at different times, my temperature sensor will be sending me different temperature signals. The temperature is varying from, let us say, 300. After some maybe 1 minute, it is becoming 350. After 2 minutes, it is becoming 400. Okay. So like that, it is varying with respect to time. And accordingly, this input voltage, because thermocouple is converting temperature into voltage. So at different times, I'll be getting different voltages. And what I want, the control system requirement is that I'm not interested in individual values of temperature. I'm not interested in individual values of voltage. But I want to evaluate the performance of my thermocouple by knowing the history for the past one hour, let us say. Please be attentive. So for the past 1 hour, it will be sending different voltages corresponding to different temperatures at different times. If I've taken readings after, let us say, after every 10 minutes, so 6 times I have taken readings for 1 hour, and at six different times, at time t1 is equal to 10 minutes, time t2 is equal to 20 minutes, time t3 is equal to 30 minutes. So voltage at t1, that is voltage at time 10 minutes, how much it was? Okay, some V was there corresponding to the temperature. After 20 minutes, it was giving me some other voltage corresponding to different temperatures. Now, as a control requirement, suppose I want to have the output voltage as the sum average of the voltages for the past 1 hour. So this OpAmp can do that integration here. It will measure, it will take the voltages at different time intervals and then add them together and give it as the output. That is what is the meaning of this OpAmp. So this is also called as integral controller also, okay, which we'll be having in the 4th unit or 5th unit. So this OpAmp can be used as integrating amplifier. So depending upon my mechatronic system requirement, depending upon my mechatronic control system requirements, I can make use of OpAmp as an integrator. Okay, let us see now the differentiating amplifier. Now what is the difference that you see? C was here and R was here in integrating. Differentiating, what is the difference now? Now the C that was here in the feedback loop, it is taken here. And R that was there, it is taken here. So forget about this dotted RN. We will discuss about it later on. So think only about R and C. So in integrator, this R was here and C was here in the feedback loop. So R was at the input side and C was at the output side in the integrating operational amplifier. In differentiating operational amplifier, what is happening? This C is taken here and this R is taken here. So the OpAmp can be used as a differentiator. Okay, forget about this dotted square. I'll talk to you regarding this later on. So think only about this capacitor C and this R, this resistance R. So there are two loops once again. Now, in the first loop, the current flowing is I. So Vin will be equal to, as I told you, in the integrating case, Vin will be equal to 1 by C integral I dt. 1 by C integral I dt. So integral is 1 by D. So Vin is equal to 1 by CD into I. 1 by CD into I. So solving it for I will be equal to CD into Vin. CD into Vin. Now, as I told you, as this OpAmp has got very high input impedance, so virtually the same current I is going through this R also. Okay. So for the second loop, what will be the equation? What is the potential drop across the second circuit? it is V out. As no current is flowing across this OpAmp. Okay. Second loop, the same current I is flowing through this resistance R. So what will be the equation for voltage output? Voltage output will be equal to I into R. So in that case, I will be equal to V out upon. So for second loop, equation for I is V out upon R, and the equation for V in across C will be I will be equal to CD into dV in, isn't it? CD into V in. So D into V in is nothing but dV in by dt. D corresponds to d by dt. So then equating these two equations, I'll be getting the equation for OpAmp as a differentiator. Friends, once again I request you, just simply don't listen and observe. Take a piece of paper. Well, these circuits, all these circuits, everything is available in Bolton. Would prefer to start reading the books and draw the sketch, and then listen to me carefully whenever I describe. So I'm trying to have on board, and so that I can explain it on the board, fine. But till that time, you just have these drawings, and let us write down the equation for differentiating amplifier. Whatever I discussed, the differentiating circuit can be produced if capacitor and resistance in integrating circuit are interchanged. The differentiating circuit can be produced if capacitor and resistance in integrating circuit are interchanged. The input current to the capacitor is IN is equal to, just now I told, C into dV in by dt. Now how this is arrived? V in, what I told you, V in is equal to what I said, 1 by C integral of I dt. 1 by C integral of I dt. The same thing. It is rearranged. Okay. So IN is equal to C into dV in by dt. So for the ideal case, hello? For the ideal case of zero OpAmp current, so at X, the current is 0, isn't it? Current flowing into the OpAmp is 0. This is also the current through the feedback resistors R. The same current I is flowing through feedback resistor R. So I told you, so this I is flowing across this, and the same I is flowing across R also. Isn't it? I is equal to V out by R. So equating these two, V out by R is equal to minus C into dV in by V in by dt. So solving for V out is equal to minus RC into dV in by dt. What is the meaning? V in is differentiated and given as output. What is the meaning of this? Differentiated and given as the output. So what is the meaning of differentiation? dVn by dt. What I'm doing practically, at every time interval, I'm finding out what is the difference in voltages. In integration, at different times, I was measuring voltages and taking the sum. In differentiation, what I'm doing, dV in, what is the meaning of dV in? dV in is delta V in. What is delta V in? At time t1, what was change in voltage, input voltage? At time t2, what is the change in input? So what I am doing practically, I am looking at the rate of change of input voltage. In integrator, I was taking the sum of the input voltages. Here what I am doing, I am seeing, I am observing for the past 1 hour, whatever was the voltage difference, what was the rate of change of voltage? Maybe considering the same case of a temperature control system, furnace temperature control. What I am getting as output now, I am observing the past data for 1 hour. What was the rate of change of temperature? It will be projected as rate of change of voltage because the temperature is getting converted into voltage by a thermocouple. Okay, so for the past 1 year, what was the rate of change of temperature? 10 degrees per minute was the rate of change of temperature. So corresponding to 10 degrees, let us say 1 volt per minute is the rate of change of voltage. So that rate of change of voltage I'll be getting through this differentiating amplifier. Now this history of the transducer data can be utilized for taking appropriate control actions later on. Okay, so the significance of that, this dotted R is mentioned here. At high frequencies, the differentiator circuit is susceptible to stability, so it tends to become unstable, and some external noise problems are there. So to suppress this instability and noise, the solution is to add an input resistor Rin to limit the gain at the high frequencies and reduce this instability and noise problem. So to reduce the instability and noise problem, we have to introduce this Rin as a stabilizing resistor. I think, friends, we'll stop for